Okay, so we've got another correlation here. Um, as before, we're going to look at which kind of correlation we can do with this one. So we're going to look at a few tests. The study here is we measured how much revision people did in terms of the number of hours they spent revising on a particular topic, and then we measured exam performance. So again here, revision in terms of hours, that is a ratio scale, because if they spent no time at all, it would reveal itself as no hours. And exam performance here, difficult to say again, probably ratio, but definitely interval. So we can use a Pearson correlation, which is the parametric version, if the data are suitable to do that. So let's have a look at the data and get the frequencies up and find out whether the data is skewed. So put both of them in because I want to know whether either of these two variables are skewed, and we can ask for charts. Let's get some histograms, show normal curve as usual, and then we click statistics and we can ask for skewness down here. And we continue and we try to find the output. Where is the output? Okay, so looking at the histogram, we can see that the time spent revising has a relatively strong looking positive skew. The tail is right up in the high numbers here. I mean, a lot of people are doing very little exam revision down here, with a few people spending, or probably just one person spending a lot of time here. So we've got a positive skew here. We might even have an outlier. We will check. The exam performance looks relatively normal though. Again, we don't expect a perfect normal distribution. Look with the blocks with so few participants, but we've got, it looks, most people clustered around the middle, somebody down here, and tending to tail off towards the extreme ends. So we're getting fairly few low scores, not that many high scores, with most people doing kind of scoring reasonably about the 60% mark. But let's have a real look at this to see whether these are acceptable or unacceptable skewness levels. Looking at exam performance, again, if you were to multiply, hardly worth saying, isn't it, 0.5 by 1.96, which is how you work it out, you would get something substantially bigger than 0.016, because the standard error of skewness itself is actually bigger than the skewness statistic. So our eyeballs are correct. This is quite a nice normal distribution. Most people around the middle. Not perfect, but you very rarely get a perfect distribution. For the time spent revising, again, our eyeballs are correct. There's a pronounced positive skew here of 2.6, and clearly 2.6 or 2.7 rounding up is more than twice the size of 0.5. So if you were to multiply 0.5 by 1.96, then that still wouldn't be anything like as big as the skewness statistic here. So we have to say that this particular variable is unacceptably skewed. It's skewed beyond the p less than 0.05 level. So that means that we can't use a parametric statistic, or we shouldn't use a parametric statistic. And notice that this is the case. This variable is fine, but one variable, if you include it in the analysis, if only one variable is skewed, then you can't use the parametric statistic, the Pearson correlation, because the parametric assumptions are violated. It only takes one variable in a test to do that. Okay, so we've done all this stuff here. What we can do now is simply to see whether there's a significant relationship. So we might wish to do a scatter plot beforehand. Again, doesn't necessarily tell you that much more. We'll just put these in this way. And then we click OK. And there's not an awful lot going on. It seems to be the case there's a slight kind of increase this way. There seems to be a very weak positive relationship, whether it's significant or not with this number of participants, not sure. So let's do the test. So we've got to correlate, bivariate, because we've got two variables, put both variables in there, and we can't do a Pearson, so we'll use a Spearman correlation and we'll stick with it on two-tailed. Now, what we found here is a non-significant result. Again, SPSS gives you at least three things which aren't terribly helpful. It gives you the correlation between time and itself, the correlation between exam performance and itself, and it gives you the time spent revising and exam performance twice. So just find one of these. Looking at the significance level, this is not less than 0.05, so we would say that this does not meet our criterion of being a significant relationship. Now, interestingly, the size of the effect of 0.4 is a moderate effect, but because it's not significant, we can't do anything about it. The first kind of fence is whether it's significant. If it is significant, then we can start commenting on the effect size. If it is non-significant, it makes no sense to, because we have no evidence from this data that this is just not a random accident, that these data aren't analysed through randomness. That's what the significance means. So we don't comment on effect size really unless the data are significant. If we were, however, to get more people to do this, given this effect size, and if the people who did this study kind of generally scored in the same way that these guys did, if we had more than 20 people, if we doubled it to 40, we might start getting a significant effect, because obviously the more participants you get, the more sure you can be that an effect is a reliable one. So that's a possibility. But what we'd report here is that there is no significant difference between the two variables. There is no relationship between exam performance and time spent revising. Now, I have to emphasise very strongly that we made these data up, so please don't be using this as evidence to not revise. Unfortunately, I probably should have made the data up to make a kind of more positive message about the relationship between time spent revising and exam performance. I apologise for that.